All right, so in this question, this is a follow-up to some previous working that we've done. Check the links in the video. We're using the information in A, and in A, they gave us both the luminosity and the flux of the star, but we really want the luminosity. We want the true brightness. And so that's the useful information in A, and you would sort of have to know that this is the sort of value that we want here. It says, and in B1, and here they gave us we had to sort of show that the temperature of the star was approximately this. And so we could calculate with sort of like the exact value. We got 6744, I believe. And so you could calculate with that. You should get something pretty close. But I'll just calculate with this value. It's approximately 6,700. And so some students that keep very accurate notes and are good at using the resources for this open note quiz may have found the Stefan-Boltzmann law, which says that the luminosity is equal to the area times the Stefan-Boltzmann constant times the temperature to the fourth power, right? So we talked about how when you change the temperature of a star, when the temperature of a star sort of like doubles, well, what happens to the brightness? It doubles to the fourth power, right? And so it's a pretty high power law there. And then you have to consider, okay, this is like a spherical star, and so it's sort of sending out its radiation over its surface area, and so the surface of a star, 4 pi radius squared. And so this is going to be the thing that allows us to solve for the radius. The area sort of matters here. When the very first white dwarf star was discovered, the only way to sort of explain how dim it appears to us was that it must be a really tiny star. In other words, its temperature was such that it's even hotter than Sirius A, the brightest star in the night sky. So it's should be a lot brighter, except for the fact that it's a dwarf star. So its radius is so tiny. And so this sort of allows us to deduce, okay, do we have this very giant star, or is it sort of a dwarf star? So this is the equation that allows us to do that. And we've seen how we can use standard candles to determine the distance, things. And as we measure the flux here on Earth and sort of relate the luminosity to that. And so let's this is the area, right, of a sphere, Stefan-Boltzmann constant, temperature to the fourth power, all that equal to the true power, the luminosity of the star. And so that equation there is the one that you need. Let's make R the subject here. So we want to kind of divide by all this stuff, 4 pi sigma t to the fourth. Do it over here, 4 pi sigma t to the fourth. Cancel those, cancel those, cancel those, cancel these. Take a square root, and we get R equal to, I'm going to write it like this. So this square root, remember, is the same thing as raising it to the 1/2. And so maybe it'd be more clear to sort of see that if I use that. So it's going to be L over 4 pi sigma t to the fourth. But I want the square root of all of that. So that's raised to the 1/2 power. Let's make some substitutions. The luminosity given up here, 4.8 by 10 to the 29 watts over 4 pi. Now sigma, the Stefan-Boltzmann constant, does anybody remember its value? 5.67 by 10 to the -8. And then the units, right, I kind of have to use this equation. So L equals A sigma t to the fourth. So its units are such that like watts have to equal watts, and so luminosity in watts. And so we need like watts in its numerator, but then we've got to get rid of the area, so per square meter, and we got to get rid of the Kelvin to the fourth. And so these are the units of sigma that sort of keep this equation homogeneous. It has sameness, the same units on each side. And so luminosity measured in watts, area would be in meters squared. And so we need to cancel those square meters out with the units of this constant of proportionality, right? And temperature to the fourth power would be Kelvin to the fourth. And so these units in the denominator of the Stefan-Boltzmann constant and watts in the numerator make it such that, watts equals watts on both sides of this equation. So those are the units of the Stefan-Boltzmann constant. Watts per meter squared Kelvin to the fourth. All right, so those watts are going to cancel there. And then where am I at? Sigma, so then we need temperature to the fourth. And so we're using this temperature, 6,700 Kelvin. and that's all to the fourth power. And so here, Kelvin to the fourth will cancel those. Remember, all of this is a square root, so we still need to take, to the 1/2 power. And then we're going to have meters squared underneath the radical, right? So when we take the square root of it, we'll get our meters of radius, right? So the watts cancel, the Kelvin to the fourth cancel, but don't forget to still raise this to the fourth power, right? We still have to, that 4 there is an exponent of both the value and the units, right? You can see kind of where the units are going to cancel. All right. I'll show this on the on-screen calculator for everybody's benefit to sort of see how the buttons can be pushed in such a way to avoid mistakes. It's always a shame when, if we get the physics right up to this point, but then, we do a button pushing error or something like that, and so we can't get the correct value in our calculator. So be careful with your calculations. All right, so you don't need any of that anymore, right? If you do, just pause the video and rewind it. All right, let's start with our numerator, 4.8 by 10 raised to the 29. I like to just type it in the way that it looks. I know there's like an EE key or something like that, so I don't have to hit the times 10, but kind of stuck in my ways. All right, now I'm going to start dividing by 4 equals dividing by I equals dividing by the Stefan-Boltzmann constant. So divide by, remember we need parentheses for this, 5.67 by 10 to the -8. Close parentheses, there's my Stefan-Boltzmann constant, 5.67 by 10 to the -8 equals. Now I've got to divide by, and I'm just going to use parentheses to play it safe, but if I hit 6,700 to the fourth power, it should do the exponent first before the division, right? But let's just be safe and say, I want to divide by, open parentheses, 6,700. I want to be sure that it's going to take that to the fourth power, right? That's the number I want to divide by, 6,700 to the fourth power. I think it would have done that anyway, even without the parentheses, right? Because it knows, the calculators know to use the order of operations very rigidly. So it would have evaluated that first and then done the division. But, the parentheses sort of guarantees it. And again, I'm a very careful calculator. I don't like to make a mistake with my button pushing once I've got all the working right. And now we just need to take the square root. So I could hit this button, right? That takes a square root, but I'd rather raise it to the 0.5 power. So it's the same thing. And this is what we get. A radius of 18284140582 meters. And so let's call that 1.8 by 10 to the 3, 6, 9, 10, 1.8 by 10 to the 10 meters. All right, now here comes the moment of truth where we look up the solutions in the mark scheme. So do I have that handy? Nope, maybe here. Nope, I got it. Maybe somewhere else. Dr. Francis and Dr. Schmidt, ready to talk about times arrow. I don't know how the Queen of England relates to that, but I'm sure they'll tell you.